So we're going to talk about geometric sequences and series. And so we're going to find out what a geometric sequence and series is. We're going to find the nth term of the sequence, okay? And then we're going to find the sum of so many terms, and then we're going to do this thing called the sum to infinity, which is like the last sort of thing to do, okay? Right. So first of all, come down here. What's a geometric sequence? Here's an example of a geometric sequence. We're going to do this one. 3, 6, 12, 24. What's the next one? 48. 96. Okay, and so on. Right. First of all, it's a sequence because it's just a sequence of numbers, okay? What makes it geometric? Why is it a geometric? Not arithmetic. It's not the same gap each time, so how is it going up? It goes up by the same ratio every time. Okay, we multiply by the same amount every time. Okay, you got it? So if I wanted to write down a sequence, then let's have a look like this. In general, this is how you would generally write these things. In general, the first term in the sequence is A. So I'm going to call the first term in the sequence U1. Okay, so it links in with the other notation. Okay, so the first term in the sequence U1 is going to be A. How would we write down U2? A times some ratio. Okay, so whatever the first term is, I times it by R. What's U3? It's that times by R again, so I'll get AR squared. And then the fourth term in the sequence would be AR cubed. So what I would really like to know is how to find the nth term in a sequence. If I wanted the nth term, so any term in the sequence. It would be AR to the power of n minus 1. Very good, Connor. Okay, so I'm going to put a box around this. This is how you find out the nth term of a sequence. So that's the first thing that we wanted to do. Okay, the nth term, if it asks you to find a specific term, the nth term is going to be un is equal to the first term times by the ratio to the power of n minus 1. Okay, you got it? So if we go back to this example up here, okay, what's the first term? In my example, 3. And what's the ratio? 2. So I've got 1, 2, 3, 4, 5, 6 terms there. Let's say I want the 8th term. Okay, so I want to know the 8th term, U8. So that's when n equals 8. Okay, so if I want to know what U8 is, it's going to be the first term, 3, times by the ratio 2 to the power of 8 taken by 1 to the power of 7. Okay, you got it? What's 2 to the power of 7? If I do that in the head? 128, and then I times it by 3. Say again? 384. Perfect. Okay. Any questions on that, first of all? Is everyone happy doing that? Yeah, A is the first term of the sequence, R is the ratio, and if you want to find a certain term of the sequence, you just do A times R to the power of n minus 1. Whichever one you're looking for, minus 1. Before we move on, I'm just going to... I don't think we talked about this before, but I'm going to talk about the graph of this. Now, I don't want you don't really get asked questions about the graphs of these things, but I'm going to draw a graph to help you visualize what's going on. Okay, so in this one here, for the graph for this thing we've just done here, example that one there, and in anything where it's going up, doubling, tripling, if it's tripling each time, it's just going to be a steeper shaped curve. But in general, the graph looks something like this. If I plot n against un like that, it's going to be like what we call an exponential curve. It just keeps getting steeper like that. Okay, you got it? What about another? I'll give you another geometric sequence. We'll do the same sort of thing. So this time I'm going to give you another geometric sequence. This is going to be. Let me grab a calculator so I can do this for you. Okay. I'm going to do. The first term is going to be 50. So this is another example. First one's going to be 50, and then next term is going to be 40. Next term is going to be 32. And the next term is 25.6. Okay. So, I want to know what the next term is in this one. Here. How would I do that? Well, what's A? A is 50. Yeah? And what's this one here? 40 is A times R, isn't it? A times R equals 40. So how am I going to find out what the R is? What's R? Yeah, R is 50 over 40. Which gives me what? What's 50? 50? You said 50 over 40. It's 40 over 50, isn't it? Jeez. 40 over 50, right? Which gives you what? 0.8, right. So, if you ever want to know what the ratio is, and you know a few terms in the sequence, what you can do is, here I did 40 divided by 50, and I get 0.8. You're absolutely right, 0.8. What happens if you do 32 divided by 40? You get the same ratio, because it goes up by the same each time, you see. 25.6 divided by 32 is going to give you 0.8. So this one's going up, it's getting multiplied by 0.8 each time. Okay? Someone tell me what the next term in the sequence would be. Say again? How have you done it then? Can you tell me? This is the first term in the sequence. This is the second, third, fourth. So I want the fifth term. So it's going to be 50 times 0.8 to the power of what? 4. Okay, and what do I get? 20.48. Any questions on that? What happens if I draw a graph of this one? In this one, the ratio was it was doubling each time, wasn't it? The ratio was 2. What happens if I plot a graph of this one? Plot a graph of this second one. What's that one going to look like? It starts at 50, and then it goes to 40, and it goes to 32, and then it goes to 25.6. So what's the graph going to look like this time? Starts at 50. When n is 1, we get 50. So the graph is going to do something like this. Do you agree? It's getting smaller all the time, this graph. So how can I tell if the geometric sequence is getting bigger or smaller? What is it about R? Okay, yeah. If we've got a number bigger than 1 and I times it by a number bigger than 1, it's going to get bigger, right? And if I times it by a fraction, 0.8, 0.5, then it's going to halve each time. It's going to get smaller by the ratio each time. Okay. So we call this one an exponential growth on the left. This is an exponential decay. Okay. Right. Any questions on that so far? Right. We'll come back to that in a little bit. That's quite important. So the next thing I'm going to do is what Shanice was asking about. Okay. This time I'm going to be a bit meaner, and I'm going to tell you. Right. I'm going to tell you that the second term in a sequence is, let's just call this another example, slightly harder, and this is a common question you get. I'm going to tell you that the second term in a sequence, so U2, the second term in a sequence is 400. Okay, and I'm also going to tell you what the fourth term in the sequence is. The fourth term in the sequence is 16. I would like to know what the 10th term in the sequence is. So that's the job. I want to know what the 10th term in the sequence is. Someone talk me through how to do that. So before I gave you some terms in a sequence, and we can find out what A was by looking. I can find out by R by dividing. Here I'm just telling you two terms in the sequence, two sort of random terms in the sequence. How do I find out the 10th term? If I find out what A was, first term, yeah? How am I going to do that? So yeah, I think you're... So Shanice is saying this. The second term in the sequence I can write like this, AR. So I know that the first term times by the ratio equals 400. Okay? And I also know that AR cubed, because that's the fourth term, that's another way of writing the fourth term, equals 16. Okay, you got it? So what you're saying is you want to divide these two, yeah? You want to divide... It doesn't matter which way you do it, but I would suggest we're going to divide these two things. The one with the higher power of R, you want to go on the top. Okay? So what Shanice is saying then is, if this is the second term, AR equals 400, and this is the fourth term, AR cubed equals 16, divide them. AR cubed divided by AR should therefore be 16 divided by 400. Do you agree with that? Well, what happens when we cancel now? We're going to cancel an A from the top and the bottom. We're going to cancel an R from the bottom with an R on the top, so that becomes squared, right? Okay, so what we found out is that R squared is equal to 16 over 400. So a square root now to find out what R is. So if we square root this, square root 16 is 4, and the square root of 400 is 20, isn't it? So is this a fifth? 1 out of 5? Yeah? 1/5, 0.2. Okay? Now that method always works. If you're given two terms in the geometric sequence, divide them by each other, the A's will always cancel because they've both got a factor of A in, and then the R's will cancel down to R to the power of something, and then you just root it. Yeah. So how do we find A? Well, we just look back at one of these things. We know what R is now, don't we? So we can look back at this one here, and I can say that A times by 0.2 has got to be equal to 400. So A must be 400 divided by 0.2, right? Okay, so what's A? A is 2000. So just wait, hold on a second, Harry, because you're a bit ahead, right? So now I've found out what A and R are. I asked you for the 10th term. Okay, so the 10th term would be A R to the power of 9. So, and Harry's saying this. The first term is 2000, and then it's R 0.2 to the power of 9. And what did you get, Harry? Sorry. 1.024 times 10 to the... It's a very small number. Okay, so this, because the R was 0.2, it's getting smaller every time. It's that second case over here. Something getting smaller, so it's got so small it's getting closer and closer. In fact, what this sequence is getting closer and closer to what value? 0, yeah. So it's almost there. Right. Now, so far, we've just talked about sequences. So what's the difference between sequence and a series? Well, a sequence, I'll write a sequence down like this. 3, 6, 12, 24, 48, 96. A series is me adding those up. So a series, a geometric series, is me adding 3, add 6, add 12. So it's a sum of those. That's the difference between a sequence. Sequence is just a sequence of numbers. A series is a sequence that's been added up. Okay? So the next thing we're going to look up is how we add up a geometric sequence. Okay? So this is me adding up a sequence. Okay? And what we're going to come up to, and this is a formula in your formula book, is we're going to come up for a formula for how to find the sum of so many terms. Okay? The sum of so many terms. Okay? So first of all, we talk about that notation you're asking about as well, Shanice, okay? So if I want the sum of the first n terms, we write it like that. The sum of the first n terms in a sequence, okay? So if I go back to the example I had before, here's a sequence 3, 6, 12, 24, 48. If I wanted the sum of the first 5 terms, that would be me saying 3, add 6, add 12, add 24, add 48. What does it all add up to? You get it? Okay. Now there's another notation we can use here. I can use this thing called sigma notation. And the sigma is a Greek letter that looks sort of like that. Okay. And the way it works is, it says we want to add up the sequence un. Okay. Now un, we've already talked about that, haven't we? So un is this sequence here, and I can change the n. So u1 would be the first term, u2 would be the second term, and I go all the way up to whatever term I want, n. Okay. So this thing here is saying sum up the sequence un for values of n from 1. That means go from u1, the first term, and then on the top ui to what number you want it to go to. So in this case, to n. Okay. So if this was, for example, if it said I want the sum of the first 5 terms, then another way of writing this is I want to add up from the first term to the 5th term of that sequence un. That's including the 5th term, yeah. So this would be u1 plus u2 plus u3 plus u4 plus u5. You see how that notation works? Now sometimes in the questions it'll try and confuse you a little bit. I could do a sequence, I could do a series from n equals 3 to n equals, from n equals 3 to like 5, say. Yeah? What would that be? That would be u3 plus u4 plus u5. So the number on the bottom tells you where to start in the sequence, and the number on the top tells you where to go to. Let's go right back up to here then, Shanice, yeah? And we're trying to write down a general formula for the sum of a certain number of terms. Okay? Now in general, yeah? In general, then the sum of the first n terms would be the first term, a, plus the second term, ar, plus the third term, ar squared. And I keep going until I get to the nth term, because that's where it tells us to stop, and that would be that. So that's me adding all of that up. We take the sum, and I times it by r. Okay, and if I times all of that by r, then what I get is ar plus ar squared. Can you see if I times everything through on the top by r, I start getting this. Everything goes up a power over r. Does that make sense? And that goes all the way to the end, ar, and this one that is now ar to the n rather than ar to the n minus 1. Do you get that? Okay. You got that? Okay. And then the next trick is, I take the first one, which was s to the n, s sub n, and I take away this second sequence that I wrote down. And what's going to happen if I start with this first one and I take away the second one? I get a plus ar, all of that, and I take away the second one. Well, this ar here is going to cancel with that one there, because I'm taking them away from each other. And that's going to cancel with that. And they're all going to cancel all the way down, apart from, there's nothing that cancels with the a. So I'm going to get an a there. And there's nothing that will cancel with this thing here. So I get that. Everything else gets cancelled out. Can you see that? You happy with that? And then finally, I just have to do a little bit of algebra here, and we get our answer. I'm going to factorise the left-hand side, so I get the sum of the first n terms. It's going to be 1 minus r. Can you see what I've done over there? I'm going to factorise the right-hand side to that. Can you see that? And then the sum, this is our actual equation then that you've got to remember. The sum of the first n terms, if I divide by 1 minus r, I'll just get it on its own there on the left. So I get a 1 minus rn, r to the power of n, divided by 1 minus r, and that's the formula that you need. Okay, that will tell you the sum of the first n terms in a geometric. Do you want to do an example? Okay. Should we do the example we had before? The 3, 6, the one that goes up like that? Okay. So in that example from before, we had, the first term was A, was it not? Sorry, the first term was 3. The common ratio was 2. See if you can tell me what the sum, I want to know what the sum of the first 10 terms is. Should we try it? So all you do is just use the formula. We want the sum of the first 10 terms, and that's going to be equal to A, which is 3, times 1 minus 2 to the power of 10, divided by 1 minus 2. Okay? So let's just have a look what this is. What's 2 to the power of 10, first of all? Okay. Oh, you put it all into your calculator. Let's have a look. 2 to the power of 10. 1024, isn't it? So what I've got is 3, 1 minus 1024, and that's going to be minus 1 on the bottom, isn't it? Okay. So divide by minus 1. This is just going to be 1 take away that is just going to be 3 times minus 1023, isn't it? Yeah. And if I divide by minus 1, it's just the same as putting a minus in front, isn't it? Okay. So I've got basically 3 times 1023, haven't I? 3069, did you get? 3069. Okay? Happy with that? Okay. So that's how you use the sum. Okay. Now there's one more thing that I've got to talk about, and then we'll do an exam question, okay? Sum to infinity, yeah? Okay, so now we're going to talk about this thing called the sum to infinity. Okay. Now, let's take a sequence that's going down, a geometric sequence that's going down. Okay. Let's start with something easy. Let's start. The first term is going to be 1. Okay. And then I'm going to times it by 0.8. That's going to be the ratio. So the first term is going to be 1, and the ratio is going to be 0.8. Okay? So the next term is going to be 0.8, because 1 times 0.8 is 0.8. And then I times that by 0.8. And I get 0.64. And then I times that by 0.8. And the next term of the sequence is 0.512. Okay? And this sequence is going to get closer and closer to 0. Do you agree? Okay? So listen very carefully to this. This is important. The sequence is getting closer and closer to 0. Okay? Now the series, me adding those things up, means that after a while, the thing I'm adding on is going to be essentially 0, right? Because let's just think about it like this, right? Let's do a few obvious examples. If I do the sum of the first term, it's just 1. Okay? Let's do the sum of the first 2 terms. I can do that in my head. It's 1.8 if I add those up. Okay? The sum of the first 3 terms, that's going to be 2.44. Do you agree? Okay? And then the sum of the first 4 terms, let's go to one more. I'm going to add on 0.512 onto that. 2.952. And if I keep going, like the sum of the 5th term, the next thing I add on is even smaller, and the next thing I add on after that is even smaller, and the next thing I add on after that is even smaller. Okay? So what's happening is if I draw a graph of this, for example, and this is different from the graphs I was drawing before, here I'm doing the n terms here, but I'm not plotting against the term. What I'm going to plot on the left here is the sum. Okay? So the sum is going to start at 1, when n is 1, then it's going to go to 1.8, and I'm going to get a curve that looks something like this. It's going to go up, but it's going to go up by less and less each time. And eventually, it's going to reach a value. Okay? It's going to get closer and closer to a certain number. Okay? Now the first, the bigger n, s of n gets to that number. And if I let n go all the way this way to infinity, as far to the right as I possibly can, then s of n will reach whatever this number is here. Okay? So that's the idea. We're doing something called a sum to infinity now. If I'm doing my sum from n equals 1 all the way to n equals infinity, and it's going to give me an actual value. Why can I do this on this sort of one and not on the one before? What is it about the r on this one compared to the r on the other one? Can someone tell me? What is it about the sequence compared to the sequence we had before? The numbers are getting smaller, so the thing I'm adding on is less each time. If the sequence was getting bigger and I was adding on something bigger each time, it wouldn't get closer to a number, would it? It would just keep getting bigger. Okay, can you see that? Okay. So this only works, I can only do the sum to infinity. So we're talking about this thing called the sum to infinity. Will only work, I can only do this thing when we use it when the ratio r, the thing we're multiplying by, has got to be less than 1. It's got to be less than 1. Why has it got to be less than 1? Because if r is bigger than 1, it's going to get bigger. Okay, so it's got to be less than 1. But it's also got to be bigger than minus 1. Okay, because if you have to multiply by minus 4, it would just get smaller and smaller. Yeah, but not closing on 0. Do you understand what I mean? Okay. So let me just write that a little bit clearer. So this sum to infinity only works when the ratio is between those values. Okay? That means that I do this sequence and I add on less and less each time. The further I go through the series, the less I add on each time. Okay? So what I'm going to write down here then is we want a formula for this. We've already got a formula for the sum of the first n terms, and we wrote it down to be this. Do you remember? And again, that's, as I said before, that's in the formula book. That's the sum of the first n terms. Okay? And we want the sum to infinity, alright? Now, if I was something like a half, something less than 1, 0.5, and I square it, let's say n is 2, and I square it, I'm going to get a quarter then, aren't I? It's going to get even smaller. And if r is a half and a cube it, yeah, it's going to be an eighth, it's going to be even smaller than that. So the bigger the value of n, the smaller r to the n will be. Okay, because r is like 0 point something, the bigger the value of n, the higher I raise the power on that, the smaller and smaller it's going to be. So what we're saying is, if we make n infinity, okay, then the formula essentially becomes this: a times 1 minus r to the power of infinity divided by 1 minus r. But what, can you tell me, essentially, what is r to the power of infinity? R is something small. Okay, let's just think about this. I'll make it more clear for you, okay? Let's say r is 0.5. Yeah? Which is a half. Okay? And now I'm going to do r squared. R squared is going to be a half of a half. Half times a half, which is a quarter. R cubed is going to be that times a half, which is an eighth. R to the power of 4 is going to be that times a half, which is a 16th. So what I'm saying is, notice as n is getting bigger, as the power is getting bigger, this value is getting smaller and smaller. So when n gets so big it's infinity, this gets so small it's 0. Perfect. So this formula is just going to change to the sum to infinity is going to be a times 1 minus 0. Well, what's 1 minus 0? 0. So the formula just becomes a times 1 over 1 minus r, because that r to the power of n has gone out of the equation. So that there is called the sum to infinity. So it allows you to tell me, if I keep adding them up, I'm going to get to an actual value. But it only works if r is less than 1 or greater than minus 1.